Okay, I want to give you some tips and tricks with working through a projectile problem where the projectile is launched at an angle. So in this case, this would be like if you had a projectile, maybe it's a soccer ball that's being kicked, or a golf ball, or just anything that's being launched up from one height and going up and coming back down to that same height. So this is, your typical parabolic projectile. And oftentimes the information that we're given is some sort of initial velocity, VO, and probably maybe an angle. So maybe it's like 30 degrees. In these problems, you could be given any set of information. Perhaps you're given the range, or you're told what the velocity was at the beginning or the end, or what the max height was. There could be any number of different variables. But regardless, what you're going to want to do is similar to the horizontally launched projectiles, where you're going to want to write out your variables in order to stay organized. So I have my x displacement, initial and final. I have my x velocities, initial and final, my x acceleration. And then do the same thing with my y. So I have an initial and final y displacement. I have an initial and final y velocity. And I have my y acceleration. Again, thankfully, just one variable for time. So in this case, it's a little different than the horizontally projected one in terms of the starting information. So again, I'm going to pretend that we have no numbers here. So we just have an angle, something theta, and maybe there's an initial velocity. We don't know. So what do we know about these variables? We know that the initial x displacement is 0. Hasn't gone anywhere yet. We know the final x displacement is the range. Don't know anything about that value, but I do know, that that's what it's going to be, how far horizontally it's traveled. My VXO, I don't know, but if we think about how this is my VXO, and how this side of this triangle is my VYO, I can actually solve for VXO being equal to my initial velocity multiplied by cosine of the angle. So if I do know my overall velocity, that is the diagonal velocity, then I can find my VXO. Now, as we saw with the horizontally projected projectiles, the horizontally launched projectiles, we saw that there was no x acceleration, and therefore my Vx is going to be equal to my Vxo. So that's helpful. My Yo is 0 meters. My final y is also 0 meters. Now, you have to be careful because maybe we're trying to solve for what the max height is, which would happen, halfway through the motion of this projectile. So when you're talking about your initial and final y's both being 0, that's because it starts on the ground, it ends on the ground. But there might be a circumstance where you're actually looking for a final y, at this point. Maybe it's somebody shooting a basketball and you want to know if it's at the right height to get to the net. For our VYO, very similar to VXO, I can actually solve that using my initial velocity times sine of the angle. And in this case, we have a negative 9.8 acceleration, which shouldn't be a surprise. That's gravity. But one thing that's interesting about these projectiles at an angle, assuming we start and stop at the same displacement in the y direction, at the same y height, so perhaps at the ground, goes up, comes back down to the ground. Whatever this VYO is, we should see the exact same final y velocity over here. And similar to how we have the same VXO and VX are the same, VYO and VY are going to be the same magnitude. They're just going to be opposite of each other. And the reason for that is because during the first half of that motion, when the ball or whatever is moving up, gravity is acting on it to take away its velocity. And from the second half of that motion, as it's coming back down to the ground, gravity is continuing to act with the exact same magnitude, negative 9.8. And so for the same duration, it's giving it velocity in that downward direction. So it's going to, in the end, be exactly equal. So if you throw an object up, it's going to come back down to your hand at the same velocity that it left at, assuming no air resistance. And so in this case, then, we have a lot of information before we've even really begun to mathematically analyze the situation. So when you do one of these angled or full type projectile motion problems, you want to take a second and sort of reflect upon what do you know before you even consider like the specifically given information. And that's where a little diagram, depicting the motion can be helpful in terms of showing you why it is that, our displacements are what they are, our velocities or our accelerations. So there you go. Hopefully that'll be a helpful tool to get started on these types of problems. Thanks.